Hola, hola a todos, bienvenidos. Bueno, es un placer presentar la conferencia que va a impartir la profesora Petia Radeva de la Universidad de Barcelona. Es además una gran felicidad porque es la segunda semana consecutiva que tenemos una conferencia del ciclo de investigadoras de prestigio que organizamos desde la Comisión de Igualdad del CiTIUS. Entonces, bueno, es un doble placer. Bueno, muchos de los que estáis aquí ya conocéis, incluso habéis trabajado en el pasado con Petia, entonces, bueno, el currículum es de sobra conocido. Simplemente, bueno, recordad que es una de las investigadoras más destacadas del ámbito, aparte catedrática de inteligencia artificial en la Universidad de Barcelona. Es una investigadora que participa en múltiples proyectos europeos, internacionales y en comités de evaluación. Y simplemente por dar un dato, y no voy a decir nada más, está en el 2% de las investigadoras más influyentes y más citadas del área TIC en el mundo. Así que, bueno, muchísimas gracias por estar aquí. Es un placer para nosotros y cuando quieras.
Okay. Sí, ¿se me oye? Sí. Bueno, muchas gracias por invitarme. La verdad es que siempre es un placer venir a Santiago y visitar este grupo que nos hemos encontrado y hemos colaborado muchísimos años. Si no os importa, voy a hablar en inglés, porque sí, así podemos acabar como 30% más rápido, si no pasaré 30% de tiempo buscando las palabras. So the talk today, I was thinking to talk about our last work on self-supervised learning, basically applied to one of the domains that is for us very interesting, that is food domain. My idea here is to talk about why we need to talk about to work on food recognition, what is so interesting there. Then we will go and give idea about our work on self-supervised learning, why self-supervised learning at this moment is so important. And then I will mention very fast some other works, and we'll discuss some real applications we are doing. Okay. Many of you, I guess, are working on supervised learning, right? So how many of you are working on supervised learning? Good. Almost everybody, right? So you know that today when we are working on supervised learning, it is very, very important to have good data sets, right? So we go for public data sets, and if we ask which are the most important data sets, here you can see Cypher10, ImageNet, Coco, OpenImages, MNIST, Cypher 100, etc., etc. So if we want to do something really interesting, okay, we can test our algorithms on Cypher10, but it's getting like toy problem. Okay, Cypher10 is really very, very small. So we really need to go and to work on bigger data sets in order to assure that what we really do is something interesting, powerful. Of course, all of us know the importance of ImageNet, but ImageNet, how many people of us can work on ImageNet, on 1,400,000 images? How many of us we have so many GPUs, right, in order to run? So this is a very, very big problem, how to manage, how to work on good high-end data set, but at the same time to solve this problem, challenge of computational resources. So how to do this? This is an open question. That's why what we decided some time ago, we decided to work on food domain. This is one of the reasons, and several more we will mention. Especially for food domain, we have a very nice large-scale food recognition dataset. It is composed of 1,000 of categories, and it has also several thousand of images. This paper was published in 2023 in PAMI, one of the best journals. And there this dataset was discussed, and we can see that it's representing a very nice challenges. For example, like it is, as you see, it is long tail distribution. So really how to develop algorithms that are robust enough to deal with long-tail distributions. Also, we have not only 1,000, and in fact, the extension of this data set came to 2,000 of categories. So are we able really to develop algorithms that are able to solve problems of recognizing 2,000 of categories? We also have some information about food categories and ingredients, so you also can work on very nice applications, how to manage ontologies of different categories, and so on and so on. Then it has already more than 1 million of images. So we began to work, not so much. We began to work on food recognition because food recognition domain is really very interesting and challenging. Food recognition is a relatively new domain. And if you see, for example, here, what is the number of papers published on food recognition, so you see that it is exponentially going up just less than 10 years. It is very important, especially for young people, when you work on some field, try to choose one issue, one challenge, one problem where it's not so much saturated. Because otherwise it's really, really hard, and sometimes in 3 years when you finish your PhD, you don't have time to really compete with all the state of the art. So one of the reasons also to us was that food recognition was a relatively new domain, but at the same time it is quite complex in order to really solve complex problems. So one of the reasons also why this domain is getting more and more popular is that there are today very nice challenges. The very first challenge was published in CVPR 2011 as fine-grained recognition. But then you see that 3 years ago there was the food recognition challenge published in AI Crowd. And we had also in ICCV the large fine food, where the data set we saw in the previous slide was presented as a challenge. And this year we also had the meta food workshop, where we had a challenge on 3D reconstruction. I will mention in one slide later. So on one hand, we see that this domain is really very much in the beginning compared to some other fields like autonomous driving or face recognition. And in this way, the food image analysis, we can solve really very nice problems. And that's why we decided to work on this. But why is the food recognition a challenge? Here maybe is one of the answers. Because if I ask you, for example, what is this? What do you think? Maybe it's sushi. But if we go for this, what is this? Maybe this is alg salad. Maybe it is some lettuce salad. If you go for example, for this, maybe it's carpaccio. Maybe it's some other meat. Or maybe even sometimes it's very similar to caprese salad, right? So it's really, really very, very difficult, a very tough problem, okay? It's very tough because on one hand, we have a lot of categories where we have a very different appearance of images of objects from the same class. That is, we have a very high intra-class variability, and we have very high interclass similarity. Here, for example, it is spaghettis with tomato, and this is curry sauce. And you see that they are really appearing very, very similar. And then we also have the fine-grained recognition. Here, for example, you have beans fried meat, beans fried pork, fried beans, fried long beans, and they are looking so similar. In this case, we speak about fine-grained recognition. We have also the problem of scalability. That is, if you think about what are the data sets today for food, we have food 256, where we have 256 different classes. We have food 101, one of the very first public data sets for food. It has 101 categories. We have food X251 with 251 categories. We have food 1K with 1,000 classes. If we think about in general for the image recognition, for the image classification, so usually we always think about ImageNet with 1,000 categories and 1,400,000 images. If we get for the food in average, we would have 150,000 of images and around 230 categories. So if we want to solve the problem of food recognition, so the question here is, how many classes do we expect to have in order to solve the food recognition problem? What do you think? How many classes do we need? How many different food categories are there all over the world? According to the most referenced, the most cited reference, that is Wikipedia, we have 200,000 of classes, 200,000 basic food dishes. And when we speak about basic food dishes, we don't discriminate between pizza quattro stagioni and pizza margherita. So if there is any Italian people here, they are really shocked. So, and the question here is, if we want the classifier to be able to recognize 200,000 foods, how many images do we need in order to solve this problem? So it is even much more, right? So if for 1,000 categories we need 1 million, for 200,000 of categories, we really need many, many millions. Okay? So it means that, well, this is really a challenge, and we should think also about this scalability problem. Okay? Okay, so a lot of open questions, as you see, and of course, regarding this scalability, you know that the higher the number of classes, the lower the performance is. So, of course, it's not easy at all to solve this problem. Okay. Now, if we have so different problems, different domains, we need a lot of data. As you know, today, having a lot of data is really not a problem. You go to internet, you get millions and millions and millions of images. What is the problem then? Who annotates them, right? So really, what is the difficult stuff is how to do this annotation. Okay, annotation is really the very slow and error-prone, erroneous. That is very easy to make errors in this process. Okay, so that's why self-supervised learning try to help to this challenge. Okay, so if we have complex problems, we need powerful models, and that's why we thought, okay, if today nobody believed that there will be autonomous cars on the street, but today it's considered a solved problem. Today, everybody, if you saw cars, at least on videos, cars that are able to drive autonomously on the road. We thought, well, also we should be able to do something similar for food domain. So why not having a picture with my phone, and then from this picture, my algorithm should be able to extract automatically all the information about the food types, food categories, food ingredients, and convert to nutritional composition. Okay, so that's why we are working in our group on all these trends, because for us it is also a way to go forward. Okay, so and this also reminds me very much to like 20 years ago when we were working on face recognition. So everybody, and here I think first lines maybe will help, maybe will confirm, nobody believed that face recognition will be possible, right? Face recognition in 98 was considered like really like scientific problem that people do to publish, but nobody believed that today it will be possible, right? Today, face recognition, you open your phone, right? With algorithm that is recognizing, that is verifying your face. Today, there are a lot of very highly performing face recognition systems. So today, I wouldn't advise anybody to do a PhD thesis on face recognition because it will be hard. It will be tough. So that's why we think that, in fact, trying to work on this food domain, in fact, we will be able to advance in different fields that still are considered like open for deep learning, especially. When we are thinking about deep learning, we cannot think about transfer learning. And transfer learning is not only fine-tuning. In transfer learning, you do multitask learning, you do self-supervised learning, you do domain adaptation, you do a lot of different unsupervised learning and a lot of different problems. And this is one of our research line where we show that in order to really solve the problem, to propose interesting algorithms and solutions for the food recognition, you really need to solve the problem like multitask learning, where you are recognizing automatically both categories and ingredients and food dishes, etc., because in this way, one task is helping to the other. Also, we have this other challenge that is still challenge of deep learning about uncertainty modeling. You have a lot of uncertainty in the data. You have a lot of uncertainty in the models. So how do you know where the uncertainty is coming from? From the models, from the data. But what is more interesting is how do you use this uncertainty in order to make your model more robust, okay? And this is something that we are working and have some very nice works already, solutions, but we will not have time to go deeper. But if somebody is working, happy to discuss. We also work on learning with noisy labeling, and I will mention in very short. Self-supervised learning, how to manage all this huge amount of data that are not annotated. Meta-learning, how to use information about how we learn. And some kind of related is, can we do continual learning? That is, if I have my algorithms that are able to recognize the dishes in Santiago de Compostela, and I go to France, how can I learn the French dishes without forgetting what I learned in the previous domain in Santiago de Compostela? And then generative AI. Today, a lot of expectations and a lot of noise is going around about generative AI, generative adversarial networks, nerves, and stable diffusion, and prompt learning, and foundational models. So this is another very open field with very interesting research going on. How to make efficient and model compression, how to make scaling that is how to solve this problem of scalability. Will we be able to recognize 200,000 of classes? Is it necessary? And if we want to do, maybe it's not necessary to recognize 200,000 of classes, but still, will we be able to recognize 10,000? And what kind of resources we need, what kind of computational resources we need. Will we be able to do on my phone? How to solve these problems? Multimodal learning. Today, our knowledge is multimodal. We have a lot of information that is coming in text, in video, in images, in ontology. So how can we leverage this situation in order to make our algorithms more intelligent? Explainable AI. How can we really understand what our algorithms are doing? Federated learning, another also very interesting open field of deep learning, how we can process all this information without centralizing all the data because of data protection reasons, or because of to be more efficient in training, and then how to apply to society problems, like, for example, healthcare. So can we really do some interesting application on our algorithms that can be helpful and can be addressing some challenges of the society? So I would try to mention some of these where we are working. But as you see, as I mentioned, food image analysis is very open, and that's why, and very good benchmark in order to address all these deep learning approaches, deep learning challenges. And that's why we are working on this data-centric food image analysis, think about not only about the models, but about the data. Because sometimes just thinking about the data, how are our data, what is the error in this, what are the problems of the data, sometimes we advance much more than just trying to think about another model, deep learning model with some modifications. Uncertainty modeling, because as we saw in the second slide, there are a lot of uncertainty in the images coming. Large-scale food recognition, fine-grained food recognition, learning with noisy labeling, self-supervised learning, generative AI for food volume estimation, and food ontology. So all these interesting deep learning problems are relevant for us. And in this way, we consider that trying to advance in this benchmark, that is the food domain, in fact, we are helping also to advance in the deep learning approaches. So I will go for the self-supervised learning. So what we see is that deep learning are dragons. So neural networks are dragons, but they are greedy dragons because they need a lot of data. And usually, when we have some neural networks, so we have some input, and then we put to the first layer, the information is passed to the next layers, etc. And then we make predictions, and then we compare to the ground truth, and then if there is difference, our loss function is high, so the loss is high, so we minimize the loss function, going back, optimizing the labels. What is the problem here? The problem is that we need a lot of data, so that's why we do data augmentation. But sometimes what we see is that data augmentation is not enough. Even if I create different crops and corrections and whatever, data augmentation, still we don't have enough with this data augmentation. So we go to internet, we get a lot of images. The point is that these images, they do not have labels. So if I use these images that are not labeled, I cannot compute my loss or my cross entropy loss function because I don't have ground truth. So what can I do? Well, here some people said, okay, there are a lot of situations where we don't have labels, but still we can use some kind of intuition, some kind of heuristics. Like, for example, here if I have all these words, I don't know what these words are. I don't know which alphabet even they belong to, but I already see that this and this are much more similar, and these are much more similar and much more different from this. Okay, so we can create what is called contrastive loss function that just want to minimize the difference between things that are looking similar and maximize the difference of things that look very different. Okay, so I can construct my contrastive loss function, and I want this contrastive loss function is putting together this and making separate the different classes. Okay, good. And this is basically what in the self-supervised learning is done. So we have a lot of data set. We don't have any labels for them. The idea is to use data sets in a what is called pre-training model, to make this pre-training model as robust as possible, so that solving some pretext task that is nothing related to my problem, the food recognition. But if I have a model that is very, very robust, then has been shown in the bibliography that having this model and putting in my domain where I have much less data, it will learn much faster and much better. And I will be able to solve this target task. So the question here is how to make this, how to take profit of these thousands of unlabeled data. In fact, at this moment, a lot of very strong groups and also companies are working on this, on self-supervised learning, getting a very, very nice results. So here, for example, you see that 4 years ago already, LeCun was giving tutorials explaining the self-supervised learning. And they found, in fact, what is really interesting, they found a lot of similarities between self-supervised learning and even human learning. This is the number of papers published on self-supervised learning, and as you see, it is a growing function. And the nice part is that if you do this self-supervised learning and just use then the model and in the supervised task, you use it as feature extraction and apply some KNN. Sometimes even it is as good and competitive as supervised learning models. Okay, and it was interesting that LeCun was finding this similarity between self-supervised learning and human learning. So you can imagine that in when we are babies, on where we observe babies, at the beginning, babies, they don't have any semantics. So you can, even if you explain this is car, this is truck, you don't have any channel to communicate with them, right? So when you show them, for example, a baby of 1 month, when you show him or her a truck and the truck falls down, well, there is no reaction because baby do not understand. But then after some months, they begin to predict the actions and even to be surprised of actions that occurred or that will occur. So what happens is that very, very first stages of human beings are very unsupervised because babies, they just observe what will happen. And there are some neuroscientists that are trying to understand, and they did already this parallelism, this analogy between human learning and self-supervised learning. So they saw that, in fact, in our brains, we also have a combination of unsupervised and supervised learning. So you see here, when we process the information, there are some of the part, you see this, for example, you have the ventral visual pathway and the dorsal visual stream. So when we use here this ventral visual pathway, in this case we apply semantics, okay? And we use this, we have this information that is a result of our supervised learning, where we put names, put semantics to objects and faces we are visualizing, we are seeing. But the information that is processed in the dorsovisual stream, here, this is analogous of unsupervised learning because we just process information based on motion, based on generic concepts, generic information. We are not applying the semantics. So in this way, in fact, people say that we can even explain how things occur in our brains. So one of the first works that was well known and already with a very nice result is the SimCLR that was developed and published by the Google AI teams. So they say, okay, if I have two images, okay, I can do some data augmentation of each of the image, okay, when I get this information, this image, and I do, for example, different crops, different color modification, etc. So I'm not changing the semantics. It means that when I pass through my neural network, whatever I classify by my neural network, this classification should be the same for this image or for this image. Okay? So in this case, we want that this, the output of the neural network, I don't know what this neural network is saying, but I know that for the classification, it should classify in the same way. But if I have different images, I have very high probability that these two images are representing different objects. So when I pass through the neural network, what I see is that the classification that is done by my multi-layer perceptron at the end of my neural network should say different. So in this way, the contrastive learning, the contrastive loss is measuring as making as similar, as small as possible the output of the different data augmented crops of the images, and it is making as bigger the difference between the different images. Is clear the idea? Okay, so in this case we are speaking about negative sampling because we are using different images, so we want that this difference between the different images is as high as possible. And positive sampling is when I have the same image but different crops, and when I do this different this different crops, I minimize the difference of as output of my neural network. Okay, so there are a lot of modification of these models that are using negative sampling, but also there are some modifications that are trying to use just positive sampling, okay? And they say, okay, because if I want to consider all combination of negative, that is all combination of images, different images, in this case I have exponential number of images, maybe just considering the images, the positive sampling, that is the different crops of the images, in this case I do have enough. So we have some models already that use only positive sampling, and they do a lot of modifications in order to make the algorithm robust enough. And they got very nice results. Now there is one also interesting work that is called Barlow twins. And in Barlow twins, they say, okay, if I have the images, I do different crops, okay? And I pass through the neural network. I have the final result that is kind of embedding, okay? So in this embedding, it is assumed that in some way we extracted the semantics. So just to give an idea, let us imagine that this embedding is, has 10 components, where the first component corresponds to the head of the person, the second corresponds to the legs, the third corresponds to the background, etc., etc. So what Barlow twin says is, okay, I want that this is the same image because this is positive sampling. So the first component here, the first component here correspond to the head. So I want that the head here and the head here has as similar representation as possible, but I want that a head is different from legs. So I want that the first component is as different as possible to the other components in the others. So it means that if we construct this correlation matrix between these 10 components and these 10 components, I want that on the diagonal we have zeros because they are comparing similar things, yeah, head to head, legs to legs, background to background. But I want that out of the diagonal I have as big difference as possible because head is different from legs. And in this way, what this correlation matrix is avoiding is the singular collapse of the models, because you see that if I do this model, that is, if I do this model where this embedding is 0, okay, and I ask only consider this to this, in this case, whatever I do, 0 minus 0 is 0, right? So the loss function will be 0, my model will stop learning, but I'm not achieving anything, so because I came up with a trivial solution that is not what I'm looking for, Okay, I don't want that whatever I pass here, the result is 0. So the Barlow twins is solving this problem. Okay, still the question is that even with this, you see that you try to make the difficult the life of self-supervised learning, and they still are learning very fast, still are memorizing the input, so they are doing overfitting. And in order to solve this problem of overfitting, there is also another work that is very nice that is called NNCLR, and it says, okay, if I get my images, I do different random augmentation from one side, from the other side, and then I pass through my encoder, I get my embedding, I do get the same images, I pass through the encoder, I get my embedding. Now, instead of comparing this vector to this vector, I will go and I will look for the nearest neighbor in this latent space, and then I want that the nearest neighbor is as similar as possible to this. That is, let us imagine I get here turtle, okay, I pass through here, okay, and the turtle I pass through here, okay. So what happened is that self-supervised learning are so good, learning so fast that it is relatively easily to get that this embedding and this embedding are really very, very close. Now, I will go in my latent space and I will go and will find the first point that is next to this, that is, it is supposed that is another turtle in this latent space, and then I will want to minimize these two turtles that I want to have to be as similar as possible. Okay, so in this way you make the life more difficult. Now, what we thought is that even with this, we still find some overfitting problem. So we decided, okay, why shall we stay with only one? Maybe we go and get the K and N, the K nearest neighbors. But how to compare then these K nearest neighbors? What we do is, we go in the latent space and we do the centroid of these K nearest neighbors. And if I go to the other, from the other side, on the other branch, I go there, I get K nearest neighbors. So I get the centroid of these K neighbors and the centroid of these K nearest neighbors. And then I want that all these, they are very similar. That is, they are like prototypes of turtles. Okay. Now, if we want to go even further, what we thought is that, okay, instead of doing this average, where in kind of, that you do average of all the embeddings, but then you think, okay, maybe in this embedding, if we think that one of the neurons is focusing on the head, another on the legs, another on the background, probably background is not important, okay, because turtle can be in very different neighbors. So in order to know how to compare these embeddings, what we can do is we can think about transformers. So transformers, when we pass through transformers different images, in fact, transformers, due to the attention mechanisms, learn on which parts of the images that are really important you should focus and which part of the images are not important. Okay? So it will learn that head is important but background is not important. Okay? So what we can do is we can kind of transform our representation after in this embedding in this latent space, and then using this transformer like a nonlinear distance, nonlinear transformation, and a new kind of distance where we really compare the embeddings after passing through the attention mechanism. Okay, so this is what we call all for one. Here you can see, okay, we have our online recorder. We get an image. Some details here I will not go. You go for KNN. You get the N neighbors in this latent space, and then you pass through the transformer, you get the centroid. And then you get from the other branch, okay, you go there, you come with the K nearest neighbors, and also you pass through the transformers, and then you get the centroid. Okay, and then you compare decentralized. So this is what we did, and this is what we called all for one. We presented last year in ICCV. Here you can see some results. This is the data set we are using. And here some results you can see. So we compare to different methods, and with barrel twins and NNCLR we mentioned. And these are the results using, for example, ResNet 18, and the results improve it. This is the top 1 and top 5, and on Cypher 10 or Cypher 100, we still see that the results improve it. And here you can see on ImageNet 100, that is a subset of ImageNet with 100 categories, so still results improved nicely. Okay, and here you can see how it worked. So when you do this embedding on the first iteration, you see that all the images are very, very mixed. When you do 100 epochs, you see that now you see the different categories are kind of separated. When you do 400 epochs and when you do 1,000 of epochs, you see that different classes are quite nicely separated. And you see that this is absolutely unsupervised. We never used, in no case, in order to get this separation, we never used the labels. Yeah, we just use the labels here to put the color. Yeah, so it's really, really very nice working. Good. Okay. And here you see some results. For example, on epoch 1, when you have this image, the most similar in the latent space, of course, are whatever categories. But when you put here, for example, one image of a boy, and you see that, of course, the first ones retrieved in the latent space is the same boy, but then you have other boys that are also in the latent space, although visually you see that they are looking very, very different. Okay? And here some apples, when you recover, it recovers apples, although they are quite different. Okay? Good. Well, here, for example, for kangaroo, we also recognize some mouse as kangaroo, but of course it is difficult for the algorithm to say that these are different animals. Okay, any questions until now? Okay. Okay, now I will go a little bit faster just to mention other food recognition works we are doing. So this is another work. Well, again, this data augmentation is it enough. What we do is we generate synthetic images in order to help to the problem to solve for having more and more images. Now, one of the works, for example, is thinking again on these methods that are data-centric approaches. As I mentioned, is that we really need to think of how our data are represented in the space. So let us imagine here, for example, we have these two classes, and we want to recognize these two classes. So we can think, we already train our model. So we always get some errors for the moment. For example, this brown and this red. So maybe this red seems like outlier, but these brown points are like different class. Different subset of the data. So the question here is, how do we generate our data? How do we do data augmentation? How can I help to this part of my brown class, where this part is where it is like underrepresented? Okay. Now the question here is, we call these hard examples, and these probably are outliers, and how to separate the outliers from hard examples. The question here is that often we do just data augmentation, we get all our training data and we do just synthetic examples, but if I do the data augmentation from my training data, because most of my training data are here on the right, of course, new synthetic data will be here on the right. So it will be even more difficult for my classifier to get aware that here there are some data, because I will have even less data for this part. So the idea here is to try to look and which are the errors and focus on these errors in order to do the data augmentation. So using this idea, we use the GANs, but focusing on this data. And how to find this data? For this, we use the uncertainty. Okay, so we estimate the uncertainty of our data, and then we do the data augmentation, but on the training data that have the highest uncertainty in order to help to this part of my data. Okay, this is another one work that we do. Another work, we are working on fine-grained recognition. In fine recognition, we see that there are some classes that are really, really very similar. So if I have one classifier that is trying to recognize 100 classes, and I want this classifier to do for all classes to behave in the same way, in a very generic way, but some of the classes are really very mixed, so it will be very difficult. Now the question here is, can we kind of focus on this part of my latent space and have some classifiers that are specialized on this part of the space, and then if these classifiers are helping me to solve this part of the space, then I can combine this and get the final result. So this is another work we are working, and we published some first results last years. And here you see that, for example, it is solving problems like here, for example, this is egg-roll. So the generic classifier says spring roll, the fine-grained classifier say egg-roll. It's especially helping to these classes that are really, really very similar. Okay, so here we used large language models in order to help this. I will not go into details. But the idea is to combine these classifiers that are focusing on subparts of the latent space. Okay, and some nice results for this model. Another problem we are working is on learning with noisy labeling. So as we discussed at the first slide, many of us, we are working on the supervised learning, but maybe people are not aware that if you get all the public data sets, and look at the labels, you will find 3.4% of average error in the labels. Okay, so here, for example, this is on ImageNet. What are or MNIST? So these are the wrongly introduced labels on the data set all of us we are using. So now the question here is, can we make algorithms more robust even to labels in the errors? So this is one work we presented last year in ICPR, IBPRIA, and we were happy to get the best paper award. In this case, what we do is, in order to make the model more robust, in fact, what we do is we use two models where each of the model is classifying the data, and then from the output of the data, we separate the output on highly confident and low confident data. So the low confident data are separated by from the high confident data, and then low confident data, supposedly representing the errors in the labels, are considered as unlabeled data and are used by the other model in order to classify in the best way. Okay, so in this way, both models interact, and each of the models try to solve the problem of the other model. Okay, and then they interchange. Here you see that for each of the model, you got the likelihood of the training data. You separate in two, in highly confident. This is highly confident because loss is very small, low confident because loss is very high, and then these data are tried to be classify it in the right way by the other model in order to help each other. Okay? And then we are working also in 3D reconstruction, of course. Today, this year CVPR was really like big change, because like 30% of works were only just on reconstruction, 3D reconstruction. Here we are not only interested in 3D reconstruction, but we are interested in food volume estimation. And here we use generative AI, especially we are using NERF in order to get proper reconstruction of the data. And in fact, this is what we call moments NERF. And okay. And we got we won the challenge. I'm really proud of my team. We presented to a challenge for 3D reconstruction and food volume estimation this year, and it was really nice surprise to get the first place. And now, as you saw, of course, there are very interesting and difficult problems, challenges, but also the second part of the motivation is that all these algorithms also have some very nice applications. And we also try to use these algorithms, these solutions, in order to help in some way to different problems. Like, for example, this is an European project where the food recognition is used in order to create an app for food intake monitoring of people with kidney transplants. Because these patients, before and after the transplantation, the operation, it is very important to have the proper diet in order to reduce the probability to reject the new organ. Yeah. And then we used here also another our algorithms. In this, there is one CiTIUS game that is created by this lady. If you are interested, I really invite you to go to see her TED Talk. That already is, that's 5-6 years ago she did it. She was a very prominent sportwoman, but she got a very important accident and she had to leave her career. And she had a lot of really problems with her health. And then finally, he elaborated a new, for her, a new kind of lifestyle where he put together all these aspects: nutrition, exercise, relaxation, positivity, and social environment. And this was the only way to kind of recover from her healthy problems. So she decided to create a serious game where she is also trying to help to other people. And here, for example, nutrition is one of the very important aspects for this serious game. So they are using the food recognition algorithms there. So, conclusions. I would like to say that food recognition to me is a perfect test domain and benchmark for powerful machine learning and deep learning models. It is highly underexplored problem that could convert in an important benchmark for computer vision and deep learning algorithms. We saw here that we mentioned how all for one, this algorithm for self-supervised learning is consistently outperforming the state of the art on different data sets. But also there are a lot of other applications, other computer vision problems that are very relevant for food image analysis, as we mentioned, uncertainty modeling, multitask learning, vision language models, fine-grained recognition, multi-scale classification. All these are topics that are at this moment going on in our group. And also, last but not least, multiple real applications and professional opportunities are available. So here, this is my small group. I'm really happy to have these young people that are very working very hard, and all this work is not possible without their effort day by day. So thank you very much. Thank you. If you have any questions.
We have questions in English.
Sure. O español también.
¿Alguna pregunta?
Lo que queráis. Don't be shy.
Don't be shy, seáis tímidos. Bueno, tenemos aquí creo que alguno de los becarios de verano, me parece, por ahí, no sé. ¿Alguien quiere hacer alguna pregunta?
No sé si estáis trabajando en cosas parecidas.
Creo que algunos sí, ¿no? Bueno, yo tengo una pregunta. Parece que la mayor parte de las técnicas que estáis aplicando, bueno, sin ser experta en el campo, ¿no?, que van un poco en la línea de intentar prescindir del etiquetado de las muestras, ¿no? Son sin etiquetar o con etiquetas mal etiquetadas, intentar un poco, es un poco la tendencia en ese sentido, ¿no? Supongo que para evitarse ese aspecto tedioso y conduce muchas veces a errores, ¿no?, de hacer esos etiquetados.
Efectivamente, sí. El Self-supervised learning lo que hemos visto es cómo ayudar a los modelos para poder aprender utilizando datos no etiquetados, sí. Y es un campo muy, muy, muy intensivo y con resultados bastante buenos. Y el otro tema que es complementario es lo de Learning with Noisy Labeling, es decir, hemos de ser conscientes que siempre tenemos errores porque como las etiquetas las han creado las personas humanas y las personas humanas no somos perfectos, aunque a veces nos lo pensamos, pero no somos perfectos, entonces siempre hay errores. ¿Cómo hacerlo que los algoritmos sean robustos y sean capaces de aprender a pesar de los errores? Esto es el otro tema también muy interesante.
Y supongo que son técnicas que se pueden aplicar, bueno, lo comentabas al final, la multitud de otro tipo de problemas, ¿no? No solamente reconocimiento de alimentos.
Sí, los métodos son muy genéricos y de hecho, como hemos visto, a ver, nosotros también para comparar con el estado del arte, lógicamente utilizamos los datasets públicos, CIFAR 10, CIFAR 100, ImageNet 100 y otros. Pero después también lo aplicamos a la comida porque la comida es un tema muy complejo.
Importante. ¿Alguna otra pregunta?
Sí, tengo una pregunta. Bueno. Hola. Okay.
Hola.
Sí, yo tengo una pregunta. Porque, bueno, referida a la aplicación, porque si al final uno de los objetivos últimos, no digo en esta investigación, que podría ser también, ¿no?, llevarlo a una app, a un móvil, ¿os habéis planteado pues incorporar otros sensores aparte de RGB? Por ejemplo, pues imágenes en profundidad o algún otro sensor que venga incorporado con el móvil.
Sí. Es una buena pregunta. De hecho, cuando empezamos a trabajar en esto de la reconstrucción tridimensional y incluso el reconocimiento de la comida hace años, entonces hay unos móviles que tienen también una cosa que se pone adicional que permite la señal hiperespectral. Y si tenemos la señal hiperespectral es mucho más fácil saber lo que es la comida que es. El tema es que esto primero es muy poco usable porque es una cosa bastante gruesa, entonces tenerlo a la buchaca, al bolsillo, un poco incómodo. Y por otra parte pensamos que nos gustaría que sea lo más genérico posible, ¿vale? Entonces por eso nos hemos limitado a RGB. Lo que estamos haciendo para la reconstrucción tridimensional, entonces allá lo que hacemos es estimamos la imagen de profundidad a partir del vídeo, a partir de varias imágenes, ¿vale? Para poder obtener la información del volumen. El tema de reconstruir el volumen es muy complejo, pero necesitamos, sí, nos ayuda mucho la imagen de profundidad, sí, en este sentido. Hay algunos algunos, bueno, los nuevos móviles creo que también te dan la mapa de profundidad muy, sí, pero todavía no todos los móviles, entonces por ahora lo estimamos. Sí. Sí.
¿Más preguntas?
Si no, estaré por aquí, si hay.
Comentabas en la presentación que bueno, una de las técnicas que utilizáis es utilizar la incertidumbre para seleccionar muestras, para mejorar el sistema. ¿Qué tipo de técnicas utilizáis para tratar de obtener medidas fiables de la incertidumbre? Porque lo que son los scores de los modelos no siempre son del todo fiables, ¿no?
Correcto. El tema de la modelización de la incertidumbre es un campo muy interesante y hay métodos, bueno, lo más simple es utilizar un Monte Carlo. Es decir, si yo, por ejemplo, hago diferentes dropout, entonces mi modelo si es robusto, pues un dropout, ¿no?, de 5% de todos mis pesos no tiene que cambiar de output, ¿no? Pero si mi modelo es poco robusto, pues un pequeño switch off, ¿no?, haciendo un dropout muy pequeño ya me dará resultados muy diferentes. Entonces, la forma más fácil de calcular la incertidumbre es utilizando la entropía de las respuestas haciendo diferentes dropouts, ¿vale? Otra forma de calcular la incertidumbre que es un poco mejor es utilizar un clasificador múltiple, es decir, utilizar varias redes y tener una red, un ensemble, ¿no?, de redes. Eso también se supone que si tú utilizas modelos robustos, los diferentes modelos pues te darán la misma respuesta, pero si el modelo no es robusto, pues no. Y después están las redes bayesianas, hay las redes neuronales bayesianas que ya también es otra forma de mirar la incertidumbre, porque ahí en una red bayesiana lo que tienes es en el modelo, en la red neuronal, a ver si podemos volver a una... Vale, aquí. Entonces, en una red bayesiana, este arco no es un peso, sino que es una distribución, ¿vale? Y entonces, cuanto más incertidumbre, esta distribución, la gaussiana, digamos, la varianza será mayor, ¿vale? Cuanto menos incertidumbre, la varianza será menor. Entonces, a partir de estas varianzas, tú puedes también calcular la incertidumbre de tu respuesta. Es decir, la respuesta en una red bayesiana no es no es una neurona a la neurona, sino que te da para cada una clase la probabilidad con la incertidumbre, ¿sí? Entonces, esto es otra forma de calcular la incertidumbre. Y después también, ahora también estamos trabajando con lo que se llama Evidential Learning, que son utilizando otro modelo que utiliza distribución de Dirichlet para calcular la incertidumbre. Hay diferentes métodos, sí.
Pero vosotros para esta aplicación estáis probando distintos métodos o digamos que hay uno que es el que se adecua más a las necesidades de este problema? ¿O?
Sí, los primeros utilizaban Monte Carlo, después los segundos utilizaban un clasificador múltiple y ahora estamos con el Evidential Learning, que es lo que funciona, digamos, lo que es más técnicamente es más robusto. Sí.
Gracias.
¿Sí?
¿Más preguntas? ¿No? Bueno, pues entonces estará por aquí un rato,
Sí.
así que si tenéis cualquier pregunta después podéis hablar con ella. Muchísimas gracias, Petia, una vez más.
Gracias a vosotros. Gracias.